Hello everyone, myself Mrs. Prachi Kare from Department of Mechanical Engineering, VP Baramati. Today we are going to see velocity and acceleration analysis of simple mechanism using graphical method, relative velocity method. Now let us revise some basic concepts of velocity and acceleration diagram. Velocity of a link. If a link is having turning motion, then velocity of link will be perpendicular to the link in the direction of rotation, and its magnitude will be equal to V equal to R into omega, where R is the length of the link and omega is the angular velocity of the link. Acceleration of a link. If a link is having turning motion, then acceleration of link will have two components, centripetal acceleration and tangential acceleration, and the resultant of these two acceleration will be the net acceleration of a link. Centripetal acceleration will be given by Fc equal to v square by r, where v is the linear velocity of link and r is the length of the link. So this is the magnitude, and the direction will be parallel to the link towards the center of rotation. So direction of centripetal component will be always parallel to link, but it should be pointed towards the center of rotation of the link. And the tangential acceleration Ft will be given by r into alpha, where r is the length of the link and alpha is the angular acceleration of the link, and its direction will be perpendicular to the link in the direction of rotation. So we will see this in detail when we will draw the acceleration polygon. So this is for a velocity and acceleration of a link if the link is having turning motion. Now if there is a slider in a mechanism, then velocity and acceleration of slider will be parallel to motion of the slider in the direction of motion. So we have to remember these points while drawing velocity and acceleration polygon. Now let us see example and we will see how to draw velocity and acceleration polygon for this. Figure shows a mechanism in which dimensions of various links are as follows. OP equal to RS equal to 150 mm, PQ equal to QS equal to 450 mm and RT equal to 375 mm. The uniform speed of crank OP is 180 rpm. Determine velocity of slider T, angular velocity of QS and rubbing velocity of pin Q, which is 60 mm in diameter. Also find acceleration of slider P and angular acceleration of link QS. The diagram is given here. Now let us see how to draw the configuration diagram first. Solution. Step number 1. To draw configuration diagram by assuming some suitable scale. So here we have to assume some suitable scale. So depending upon the dimensions of link, we have to take some scale. Take a note that the scale should not be too small so that you can't draw the lengths of the link which are visible, and it should not be too large that it will go out of the page of your sketchbook or sheet. So take a suitable moderate scale. So here we have taken 1 centimeter equal to 75 mm. The scale may be different with different one. Now we have to see how to draw the configuration diagram. So these are the given dimensions. With this, first take a point O. From this we have to start the configuration diagram and draw a horizontal line from which draw 375 mm offset. Now this 375 mm is the actual distance which we need to convert into scale. So convert this into the scale of 1 centimeter equal to 75 mm, and with that converted distance draw the offset of 375 mm horizontal line. Also take a offset of 375 mm vertical and draw a vertical line. This intersection will give S point. From this horizontal line, take a reference lines for 100 mm offset for the slider. Then from O, draw 45 degree, and on this 45 degree, take distance OP, which is given 150 mm. So get it converted into scale and take distance OP, will get point P. From P, in a compass, take distance equal to PQ. So PQ is 450 mm and QS also 450 mm. with the distance of PQ and QS make a arc. So PQ and QS make a arc with a compass to get point Q and join PQ and QS. Then on this link SQ, we have to locate R point. So distance is given for RS equal to 150 mm, convert it into scale and measure from S, you will locate point R. So once you got point R, take distance in a compass equal to RT to make an arc on this horizontal line to get point T. At point T, draw slider and join this RT to get link RT. So likewise, we have to complete the configuration diagram with the given dimensions. Now, step number 2, to calculate velocity of input link. So always the angular velocity of input link will be given either in terms of RPM or in terms of radian per second. So here N is given 180 RPM. From this, first we will calculate omega equal to 2 pi n by 60. So substitute n equal to 180 in this and calculate the omega. We are getting it as 18.849 radian per second. So then use the relation V equal to R into omega, where R is the length of link OP and omega is the omega OP. So here you need to substitute actual length of the link. Do not use the scaled value with which you have drawn the configuration scale. You have to take the actual value of the length of the link and multiply it by omega. It will give you linear velocity of the link. So after getting the linear velocity of the link, we have to get the scale. Now let us take a suitable scale depending upon this value. So with reference to this value, we have to choose some suitable scale. And here we have taken scale 1 centimeter equal to 0.5 meter per second. Now to draw the velocity polygon with the scale of 1 centimeter equal to 0.5 meter per second, let us see what is the procedure. So here is the configuration diagram. We have taken it for the reference here, with which we have to draw the velocity polygon. Now we have to start with a point. So take a point and give the name to the point as whatever the fixed point in a mechanism. Say O and S are fixed point. So give O and S to this point. So whatever may be the number of fixed link, there will be 2, 3 or 4 fixed link in the mechanism. All they will come at the same point OS which we have taken, and with that reference point we have to start with the velocity polygon. Then we have to draw the first is velocity vector of OP. This is a crank. So see, now it is having turning motion. So velocity of link which is having turning motion is perpendicular to link. So velocity vector of OP will be perpendicular to link. But now either you can draw it in a downward direction or you can draw it in an upward direction. There can be two vectors possible perpendicular to the link, upward and downward. So it is in the direction of rotation. So it is rotating clockwise. So velocity vector of OP will be downward because it is moving in a downward direction. Link OP is moving in a downward direction. So its velocity vector will be in a downward direction. If this link is moving in a anti-clockwise sense, means it is moving up. So in that case, its velocity vector will be upward. So velocity vector of OP should be drawn from O, which is perpendicular to OP in the downward direction. So this is the direction and the magnitude which we have calculated earlier, that the velocity vector is in a downward direction with the magnitude of linear velocity of P. Convert it into scale and take that dimension here to get the point P. So this is the velocity vector in magnitude and direction of OP. Now we come up to P. So now there is a link PQ. So we have to draw velocity vector of PQ. So velocity vector of PQ is perpendicular to the link. Again you have to draw a vector perpendicular to the link. So velocity vector of PQ will start from P and it will be perpendicular to PQ. So this is a vector which is perpendicular to PQ. So from here you have to draw either with the row line draw or with the help of the set square. Draw a line which is perpendicular to PQ and from P. But we don't know its magnitude. So just keep it as it is. Only the direction we know. We don't know the magnitude. So keep that vector as it is. But as this Q point is on PQ, Q point is also on link SQ. So Q point must lie on velocity vector of PQ also and on velocity vector of SQ also. So now what will be the velocity vector of SQ? So it will be perpendicular to SQ. So from S, draw a velocity vector perpendicular to SQ. And intersection of these two velocity vectors will give us point Q. So again I will repeat, we don't know the magnitudes of velocity vector of PQ and SQ both. So we know only direction. So we will locate velocity vector of PQ. We will locate velocity vector of SQ. And intersection of these two will give us point Q. So this is the intersection, will give us point Q. So this is velocity vector of PQ and this is velocity vector of SQ. Now we came up to velocity vector of Q. So on this velocity vector we have to locate point R. So to locate point R we have to use velocity image principle. So velocity image principle says that the ratio of length of link in mechanism is equal to their ratios in a velocity polygon. So we will take the ratios of SQ upon SR. So SQ is the actual length, SR is the actual length. Small SQ is the length in velocity polygon. So this we can measure, small SQ, this length we can measure. So these three things are known. So substitute these values, we will get the value of SR. Now here take actual length of SQ, take actual length of SR, don't take the scaled values. Here take actual length of SQ from velocity polygon. So simply measure this distance and transfer it over here. Don't convert it into scale. And then you will get the value 2.233 which can be directly transferred here on the velocity polygon. So here we got a point R. So we come up to R. So then there is a link from R, there is a link RT. So velocity vector of RT is perpendicular to the RT. So from R we will draw a velocity vector which is perpendicular to RT. Again we don't know its magnitude. So simply draw the velocity vector. See, in the velocity polygon only the magnitudes of velocity of crank will be known. The velocity of any other link is unknown. It has to be located by the intersection of velocity vectors of the two links. So same way here you have to locate this velocity vector of RT which is perpendicular to link RT. Then T is on RT, but likewise T is a slider also. So for slider velocity vector is parallel to motion of slider. So motion of a slider is horizontal and slider is having the motion with respect to fixed link. So from fixed link, that is from point O in a horizontal direction, we will draw the velocity vector of slider. And the intersection of these two will give you point T. So this is velocity vector of TR. And this is velocity vector of VT. Now we have to calculate velocity of slider T, that is vector VT. So simply measure this distance O to T multiplied by scale. It will give you actual velocity of OT 1.15 meter per second. Now we have to get angular velocity of link QS. So we know V equal to R omega. Using this we can find omega equal to V by R. So you can find out velocity of QS. So simply measure this distance QS, this vector. Measure this, multiplied by scale, it will give you velocity of QS. Divided by length of link QS, it will give you angular velocity of QS equal to 7.444 radian per second. Same way we have to find out angular velocity of link QP. Again omega QP is equal to V QP divided by length QP. So to get VQP, measure this velocity vector QP, multiply it by scale and divide it by length of link QP. It will give you the same value at 7.444 radian per second. Now next is to calculate rubbing velocity at Q. So rubbing velocity at Q. So now at point Q, there are two links, PQ and QS, or you can say QP and QS. So the rubbing velocity will be omega QP minus omega QS into radius of the pin. But omega QP and QS are same, that's why it is coming out 0. So likewise you can find out rubbing velocity at point Q. Now we have to see the acceleration polygon. For this, first we need to calculate the acceleration of the various links. So for this we need to prepare this table which will include link, length of link, velocity of link, centripetal acceleration and tangential acceleration. So here we have the various links as OP, PQ, SQ, FT, RT and slider. So these are the lengths of the link which are given. These are the velocities of the link. So this you can find out from the velocity polygon. These links you have to find out from velocity polygon. So multiply these vectors into scale. It will give you the velocity of all the links. Now centripetal acceleration is equal to V square by R. So V is the velocity, square divided by R. It will give you centripetal acceleration. So this is magnitude and the direction will be parallel to the motion. Now here tangential acceleration will be 0 because alpha is 0. As crank is rotating with uniform velocity, it is given. It is mentioned in a problem statement that crank rotating with uniform angular velocity. So that's why angular acceleration will be 0. So the crank will not have tangential acceleration. So it will have only centripetal acceleration. Tangential acceleration will be 0. Now for link PQ, you have to take centripetal acceleration equal to V square by R. Again calculate V square, that is 3.35 square divided by 0.45. It will give you the magnitude. Now for tangential acceleration, magnitude is unknown. Only we know the direction, that is perpendicular to the link. So we don't know magnitude of tangential acceleration of any of the link. We will only know the direction, that is tangential or perpendicular to the link. And we will know the centripetal acceleration of all the links as we know all the velocities of all the links. So using this, calculate the centripetal acceleration of SQ, centripetal acceleration of RT using the formula V square by R. And for these two also, we will not know magnitude of tangential acceleration. Only the direction is known. This is to be located by having the intersection of the tangential components. And then for the slider, there will not be any centripetal acceleration because there is a straight line motion. There will be only slider having linear acceleration and that will be parallel to motion of the slider. Again, its magnitude is unknown. So that is to be located by intersection of the vectors. So now let us see how to draw the acceleration polygon. So now again you need to take a scale for acceleration polygon. So this scale depend upon the values of centripetal acceleration. So take a note of this, that scale of configuration diagram, scale of velocity polygon and scale of acceleration polygon all are different. That depends upon the values of the dimensions of the link, values of the velocity of the link and values of the acceleration of the link. So three different scales you need to consider for configuration diagram, velocity polygon and acceleration polygon. So this is the configuration diagram which we have drawn. With reference to this, we will draw the acceleration polygon. And the second important thing is to draw the acceleration polygon, you need to draw the velocity polygon first. Without drawing velocity polygon, you cannot proceed to the acceleration polygon because you need to calculate the values of centripetal acceleration. And to calculate the values of centripetal acceleration, you need to calculate the velocities. And to calculate the velocities, you need to draw the velocity polygon. So always first complete the configuration diagram, then complete the velocity polygon, and then go for the acceleration polygon. Now again you have to take a reference point. So whatever are the fixed link in a mechanism, that is to be considered as a reference point. So here O and S, these are the fixed link in a mechanism with which we will start our acceleration polygon. Now we will always start with the crank. So OP is the crank. Now remember, always you have to draw centripetal acceleration first, and then you have to draw tangential acceleration, and then its net resultant will be the total acceleration. So first we have to locate centripetal acceleration of OP. So centripetal acceleration of OP magnitude we have calculated already in the previous table. Now the direction is parallel to the link. So parallel to the link means parallel to OP towards the center of rotation. So what is the center of rotation for OP? O is the center of rotation for OP, means downward. So acceleration is parallel to OP in downward direction. Means from O you have to go downward. From O you have to draw a parallel line. But you can draw a parallel line from O upward and from O downward. So why to go downward? Because centripetal acceleration of OP will be towards O, that is downward direction. So from O you will draw it in a downward direction. That will give you point P. So this is the direction and the magnitude which we have taken already in the table. Convert it into the scale and you will get the centripetal acceleration of OP. After locating centripetal acceleration of OP, you have to draw tangential acceleration of OP. But as we have seen earlier, crank is rotating with uniform angular velocity. So tangential acceleration will be 0. So we will not draw any tangential acceleration as it is 0. So the total acceleration is the same. That is the centripetal acceleration. Now we come up to P. Then we have to go for PQ. So now first you have to locate centripetal acceleration of PQ. Then you have to locate tangential acceleration of PQ. Now see, centripetal acceleration of PQ is parallel to PQ towards the center of rotation. Now for PQ, P is the center of rotation. Now how to decide center of rotation? So if I say link QP, then Q will be center of rotation. If I say link PQ, then P is the center of rotation. Now we have started with O, we have located OP, then we are moving to PQ. So we have to follow the sequence. So as we are saying link PQ, P is the center of rotation. So means in a upward direction. So from P parallel to PQ in upward direction. See, if Q is center of rotation, then from P you will go in a downward direction. Okay. But here P is the center of rotation, means see the direction, it is towards P. It should be towards P. Towards P means upward. So from P in upward direction, there will be the direction of PQ. Don't get confused that towards P means you have to draw it over here. Towards P it's only up to this area to have the upward or downward direction. Once you get upward direction, then from P you draw it in an upward direction. So the magnitude is known. Take it from the table, centripetal acceleration, multiplied by the scale, and with that magnitude and this direction, locate point Q dash. So this is the centripetal acceleration of PQ. At the end of centripetal acceleration, you have to draw tangential acceleration. So the direction of tangential acceleration is perpendicular to PQ. So perpendicular to PQ from Q dash. This is the tangential acceleration. Now again you don't know the magnitude. So leave this vector as it is. Because you can't locate this point Q. Because you don't know what is the magnitude of tangential direction. So just draw this vector and keep it as it is. Now Q point is on link PQ. Also Q point is on link SQ. So we will leave this vector as it is and now we will move with link SQ. So keep it as it is. Now come to SQ. So locate now centripetal acceleration of SQ. So centripetal acceleration of SQ is parallel to SQ towards the center of rotation. Now see, I am saying link SQ means S is the center of rotation. So here what is the direction? Towards S. Parallel to SQ towards S means upward. So from O in upward direction. Why upward? Because it is towards S. Centripetal of SQ will be towards S. That is upward. So from O in upward direction parallel to SQ there is a centripetal acceleration. The magnitude is to be taken from the table, multiplied by scale and take this magnitude. So it will give you point Q1 dash. So this is the centripetal acceleration of QS. Now at the end of centripetal acceleration, start drawing tangential acceleration of SQ. So again the direction of tangential acceleration of SQ is perpendicular to SQ, but its magnitude is unknown. So draw the vector from Q1 dash which is perpendicular to SQ or which is perpendicular to the centripetal acceleration. And where these two intersects, it will give you Q. So how to locate Q? Locate tangential of PQ, locate tangential of SQ. Where these two will intersect, it will give you point Q. Now if you take this, it is the tangential of PQ. This is the tangential of QS. Intersection gives you final point Q. And this is the total acceleration of PQ. See, centripetal of PQ, tangential of PQ and net resultant of PQ. Similarly, centripetal of QS, tangential of QS and resultant of QS. So, one link is giving you 3 acceleration component. One link is giving here 3 acceleration component. Centripetal, tangential and net acceleration. So we have located acceleration of OP, PQ and QS. Now here R is on SQ. So here also R should be on the net acceleration of SQ. Now we have to locate point R. So again we have to take the same image principle that SQ upon SR is equal to small sq upon small sr. Capital SQ and capital SR are the actual length of the links in a mechanism. So take this actual length of the mechanisms. Small SQ you can measure from here. So directly measure this distance. Don't convert it into scale. Okay. Take it as it is and substitute over here. It will give you SR. So whatever the answer you are getting here, directly you can transfer this SR. So again I am repeating, while taking SQ and SR, take the actual dimension. While taking this SQ, measure this SQ, take it as it is over here, calculate SR and whatever the answer you are getting, just locate it for the R point. After getting R point, now we have come up to this R. Now we have to locate acceleration of RT. So first we have to locate centripetal acceleration of RT. So centripetal acceleration will be parallel to RT. Now what is the center of rotation? R is the center of rotation. As I am saying, RT. So link RT will have R as the center of rotation. So centripetal acceleration is parallel to RT towards R, means towards left. So from R parallel to RT, draw a line parallel to RT towards left. Don't go towards right. You have to go towards left. So, and what is the dimension? The magnitude. Take it from the table of the centripetal acceleration. Convert it into scale value and take this centripetal acceleration. Now this is T dash. This is the centripetal acceleration. Now from here you have to draw tangential acceleration of RT. So tangential acceleration of RT perpendicular to RT. Again you know only direction, magnitude is unknown. So keep it as it is. Keep this vector as it is. We can't locate the T point now. Now go as T as a slider. As T is on RT, T is also slider. So keep this vector incomplete as it is and go to the slider. Now locate the acceleration of slider. Acceleration of slider will be parallel to motion of the slider, that is horizontal. Now slider is sliding on a fixed link. So from fixed link, draw horizontal line. Where these two will intersect, it will give you point T. And this is the acceleration of slider. And this is the total acceleration of link RT. So likewise, you have to complete the acceleration polygon. Now we have to calculate acceleration of slider T. So simply measure this dimension, acceleration of slider, multiplied by scale, it will give you acceleration of slider 13.5 meter per second square. Now angular acceleration of QS, we have to find alpha QS. So we know the relation between tangential acceleration and angular acceleration. Ft is equal to r into alpha. R is the length of the link, alpha is the angular acceleration. So using this relation, we can find alpha. So measure Ft. How to get Ft? So simply measure this Ft, this value Qs. Okay, multiply this by scale, it will give you Ft as 34.5 meter per second square. Substitute in this relation, substitute length of Qs, solve this, it will give you alpha Qs. That is angular acceleration of Qs equal to 76.667 radian per second. So in this way, you can calculate acceleration of slider, angular acceleration of link by locating the various acceleration component on acceleration polygon. The thing is to remember is that measure the distances of the vector. Don't forget to multiply these by the scale to get the actual values of the acceleration vectors. Thank you.